Here's an overview of this Excel sheet that can be used to compute adiabatic flame temperatures for combustion reactions. We have here on the left the chemical species that are included, and they're reproduced on the top and the bottom in two different temperature ranges. These data here are coefficients, polynomial coefficients for a curve fit for heat capacity, enthalpy, and entropy. So as a function of temperature, we have the heat capacity for CO that depends on this reactant temperature here and the gas constant, and that'll give the heat capacity. For enthalpy, similarly, we have the gas constant, the coefficients for CO at this temperature. And then the same thing for entropy here. So it's for all of these species. And if you're in a temperature range that's between 300 and 1,000, then you would use these values. And if you're in a temperature range that's between 1,000 and 5,000 Kelvin, then you would use these values here on the bottom. Okay, and we've got these set up so that they refer to the reactant temperature here, or they can refer to the product temperature right here. Now at the bottom, we can specify the reactants. So if we had a flame that was using ethylene, we have C2H4 with 1 mole, O2 with 3 moles, nitrogen with 11.28 moles. So this would be a stoichiometric ethylene air mixture. And then the corresponding products are 2 moles of CO2, 2 moles of H2O, and 11.28 moles of N2. Then the enthalpy of these reactants is the moles times the enthalpy of that species. So C2H4's enthalpy is here 52543, and so we multiply that by the number of moles, and we do that for the other species. O2 is 3 times the enthalpy of O2, N2 is 11.28 times the enthalpy of N2, and we know that the reactants we're assuming are between 300K and 1,000K, so they all refer to these upper values up here. And then the total enthalpy of all the reactants is simply the sum of that column. So this gives us this total enthalpy. We do exactly the same thing for the products. So if we put in like, I don't know, 1200 Kelvin for the products, for example, then the products are 2 moles of CO2 times the enthalpy of CO2, 2 moles of H2O times the enthalpy of H2O, 11.28 moles of N2 times the enthalpy of N2, and the total product enthalpy is the sum. So we have the sum, we have the enthalpy of the reactants and the enthalpy of the products. These enthalpies need to be equal, and we make them equal by adjusting the temperature until we get these two cells to be the same. You could do that by trial and error. 1200, it's too low, negative. So let's make it, say, 2000. It went up a little bit. Let's make it 2200. Let's make it 2500. Okay, let's make it 2700. And you can see how those things change. Now we're too high. It's awkward to do that by trial and error, of course. So we'll go into the data tab here and just do a what-if analysis. And we can simply do goal seek by setting cell, that one, to a value equal to the green value, 53326.823, by changing our unknown product temperature, and hit OK. And you can see it finds a solution. These two cells are now the same, and this is the adiabatic flame temperature for that system. And this does this without any assumptions on heat capacity or enthalpy. This is fully temperature dependent, but we don't have to do the integration ourselves because it's built into the enthalpy values of the species. That's already effectively been done for us. So that's a quick way to do this. You can see the reaction, the stoichiometric reaction is listed here, and the approach, goal seek, set the orange value, the orange cell to a value of the green cell by changing the red cell. Kind of takes you through how that works.